Okay, so the rational number has been countable. So what does countable mean?
Since you can you can list it out.
Okay, yeah. So there's a couple different kinds of infinities.
Yeah.
Do you remember the name of the mathematician who's originally studied infinities?
No.
The mathematician's name was Cantor.
Cantor.
So what we're going to do, so if you want to prove something's countable, basically you want to be able to match it up.
With something that we know is countable.
Yeah, and the thing we know is countable are the positive integers.
Yeah.
Okay. So you want to be able to match it up with the positive integers. So what we do, and then I believe this was Cantor's argument, is we say, okay, well, I'm going to represent all of the rational numbers as lattice points in a grid. So here's going to be 1, 2, 3, 4, 1, 2, 3, 4, 5, etc. Yeah, so I put a 5 there. And here I have my lattice points. And I could say that this one represents, I could always say the fraction represented by the lattice point is the x value divided by the y value. So this would be 3 over 1. And this point here, 4, 3, would be the fraction, would represent the fraction of 4/3. So every rational number is going to be represented
On this grid.
on this grid. Can you say anything else about what this grid is
All
going to
the integers.
All the integers are going to be
down
there?
here.
Because they're in the first row.
Then we have the integers divided by 2. Integers divided by 3.
Yeah.
Divided by 4. Divided by 5.
Does every rational number appear in this grid?
Yes.
It does.
Does it appear uniquely in this grid, or does it appear more than once?
It appears.
I believe more than once.
Give me an
because
example of a number
So we
Like-
have
that you're going to see more than once.
4/3 and 8/6.
or three and 6/2.
3 and 6/2, yeah. So we're going to not just see the numbers exactly once, we're going to see the numbers lots of times. So this, in a way, this has more than all the rational numbers. It has all the rational numbers multiple times.
I
Yeah.
think it is all of them infinitely many times.
That's exactly right. It has all of them infinitely many times.
Yeah.
So this grid represents way more than the rational numbers, but it has all of them.
It does.
Every rational number appears on this grid. Why?
Yeah, because you're just going with the integers here, and a random integer divided by another random integer is going to be rational.
Okay.
It's sort of the definition of a rational number.
Okay, cool.
Yeah.
So now the question is I've got this sort of doubly infinite grid. So it's infinite in this direction, it's infinite in this direction, and I need to figure out a way to walk through this where I can say, hey, this point on the grid is like, the 37th point or something like that. The problem is if I walk this way,
You'll never.
I never get up to the second row, and if I walk this way, I never get over to the second column. So I have to figure out a clever way to walk through this grid.
Snake through it somehow.
You should sort of zigzag.
Draw. Actually, here, you did the last one. You draw how you think you might be able to do this.
So
Here, start here. This is the first one.
we sort of snake sort of like this. Then it would continue up here and it would come back.
Okay, so this sort of snaking way seems like an interesting way. Can you grab a different colored pen, and I'll have your brother also do a snake. Maybe you have the same idea. Maybe you have a different one.
This was kind of my idea of it.
So your idea is exactly the same.
Yeah, it's just this is how I would have done it.
All right. So I think I'll show you. Let me just erase. I think traditionally, the snaking idea is exactly the right idea, and I'll show you. I think how the usual snake works.
Yeah, I think I sort of see it.
So actually, I'll do it with black so I don't infect this other marker. So you start here, you go over, up, and then you just go like this. So you don't have those So you always just kind of go down those diagonals and up those diagonals. So you don't have to, your way is fine, by the way. You just have to, in your way, it was a little more complicated. Oh, I missed a dot here. I have to go back and get it.
Yeah.
But here, instead of going, you went up here. So instead you go across
Yeah.
when you hit. And then here, when you get to the last one, coming up, you go up. And then
Makes sense.
down, across, back up, down, across. And then, do I hit every point?
You did.
Yes.
Okay. Although it might not be easy, if I asked you what's like the 10,000th grid dot you run into here,
You can find it.
you could find it because our diagonals have 1, then they have 2, 3, 4, 5.
And 6.
So you can see where you are
Relatively easy.
relatively easily. And then you can see that quite surprisingly, I can actually list the
The points.
rational numbers.
As integers.
I can pair them up with the integers. So I can say like 3 halves. In this idea, I could say 3 halves, which is 3 divided by 2 here, would be the 1, 2, 3, 4, 5, 6, 7, 8th rational number.
Wow.
Now, they wouldn't be in the right numerical order.
But they would.
But you can still pair them up. That's,
Still pair them
that's
up.
what matters.
Yeah.
Wow.
So that's neat. So that shows that the rationals are indeed countable.
Nice.
Okay. It's a fun video.
Yeah.
It's a fun video. There's a lot of stuff in that video. And actually, do you remember our friend Joel David Hampkins?
Yeah.
He studies this. This is the work. This is the field that he's involved in.
Yeah.
Set theory. All right. Good job, guys.